So today we're going to review an algebraic technique that you learned in a previous algebra class using the method of elimination to solve a system of linear equations. And then we're going to learn a new method for solving those kinds of systems that uses matrices. All right, so when you're solving a system of linear equations by elimination, there are three basic steps. You replace one equation by the sum of itself and a multiple of another. You can interchange two equations, and you can multiply all the terms in an equation by a non-zero constant. So for example, here's a system of two equations and two unknowns. We're going to solve it using elimination. There's just a teeny little tweak because I'm going to make it match up to this new method that we're doing, so it might look a teeny bit funny, but you'll recognize it. All right, so let's say we want to eliminate the x's, right? I'm going to do solve by elimination. I want to get rid of the x's. Here I have a 1x, here I have a negative 2x. What could I multiply that whole first equation by so that when I add the two equations together, the x's cancel? 2. You were going to make 6's? Don't worry about it. 2. All right. So my new equation 1 is going to be 2x plus 10y equals 14. And then I'm not going to change equation 2. It's going to be negative 2x minus 7y equals negative 5. So that's, I did this third thing I'm allowed to do. Multiply all equations, all the terms in an equation by a non-zero constant. All right, then I'm going to add them together, and I'm going to replace one of the equations with that sum. Okay, so when I add these together, the x's cancel, and I get 3y equals 9. This is going to be my new equation 1, right? So I can replace one equation by the sum of itself and a multiple of another. Okay, sorry, that's going to be my new equation 2. So my new system, equation 1 stays the same as it was. X plus 5y equals 7. Or 2x plus 10y equals 14. They'll have the same solution, so either one. And then I'm going to replace equation 2 with 3y equals 9. Then I'm going to use my third thing I'm allowed to do again, multiply all the terms in an equation by a non-zero constant. What should I multiply equation 2 by? 1/3. Yeah. So multiply this by a third. So my new equation 2 is that y equals 3. So my equation 1 stays the same. Equation 2 becomes y equals 3. And then you can back substitute to solve the first equation. So that says x plus 15, 5 times 3 is 7. And so x is negative 8. So it feels familiar, right? We've all done that. So just to point out, okay, in that system of equations that we solved, all the important information is contained in the coefficients and the constant terms. The names of the variables x and y are not important. Okay, so we can represent the system using a rectangular array called a matrix. So in the first column, I'm going to put coefficients on x. So my first equation, it has a 1, second equation, negative 2. Second column is going to be my coefficients on y, 5 and negative 7. And my third column, after a vertical line that represents the equal sign, is the constants, 7 and negative 5. So that matrix we just created has, we call it a 2 by 3 matrix because it has 2 rows and 3 columns. And you always do rows by columns. You can remember like remote control, just a little mnemonic to remember, always rows, columns. So this has 2 rows, 1, 2, and 3 columns, 1, 2, 3. You can perform the same basic maneuvers on the matrix that we did on the equations. These are called elementary row operations. You can do replacement, where you replace one row by the sum of itself and a multiple of another row. You can interchange two rows, and you can scale a row by a non-zero constant. So I'm going to solve our original linear system using a matrix and row operations, and it's going to mirror what we did up here. So I start with my matrix, 1, -2, 5, -7, -7, 5. And again, that vertical line just represents the equal sign. X's, Y's, constants on the other side of the equals. Your equations have to be set up in this format to use the matrix method. X's, Y's, constants on the other side of the equals. Okay, so I have a 1 here. I want to get rid of the -2. That's what we did before. We tried to get rid of the x's, so we multiplied the first equation by 2, added it to the second equation. So I am going to get rid of, I'm working on this -2. I want it to be a 0. I want to replace row 2 by adding a multiple of another row to it. Okay, so row 2 is going to get replaced with row 2 plus 2 row 1. That'll make that -2 in the spot I circled in blue will become a 0. So you can write this out at first if you need to. So row 2 is -2, -7, 5. Add to it twice row 1, so that's 2, 10, -14. And you get 0, 3, 1. Oh, that's supposed to be a 14, sorry. 0, 3, 9. What's that pen thing? Go away. New version of the software. Okay. Apparently I can't move it. Just leave it there. So 0, 3, 9, that's my new row 2. So I said row 2 was going to get replaced by itself plus a multiple of another row. So my new matrix looks like this. 1, 5, -7. Row 1, even though you multiplied it by 2 here, that's just a step in how you're changing row 2. Row 1 is actually staying the same in the next step of the matrix. Row 2 changes to 0, 3, 9. Was it? Oh, no. It should be, 1, 5, 7, -2, -7, -5. Okay, so that's right. This should be positive. Got it. Thank you. Thank you. Right, so that should have been 2 row 1. That should have been positive 14. Still comes out to 9. Okay. Thank you. All right, so now I'm going to scale row 2. So my next step is that row 2 is going to become 1/3 row 2. So my next matrix is going to be 1, 5, 7, 0, 1, 3. And at this point, I can translate this back to equations and then back substitute. So this first row says that x plus 5y equals 7. And my second row says y equals 3. It says 0x plus 1y equals 3. And then back substitute. So we have x plus 15 equals 7. X is negative 8. So this is the general idea. This was a really short example because it only took 2 steps. But you can basically swap any 2 rows you want. Like I could have put the first equation on top, the second equation on top, first equation on the bottom, doesn't matter. You can always swap rows if you want, if it helps. You can replace one row by the sum of itself and a multiple of another. So I replaced row 2 with the sum of itself and the multiple of row 1. And you can scale all entries in a row. The goal being, right, to get your bottom equation so that it's solved. So that you have 1 something, like 1 on the last entry in the bottom, and then a constant. All right, so just a couple of notation things. When you have one unknown, we typically call it x, 2, x and y, 3, x, y, and z. But after 3 unknowns, we've run out of letters. So as a matter of common practice, we use x sub I to name each unknown. So for 3 unknowns, instead of using x, y, z, we would use x1, x2, x3. So general algorithm for solving a system of linear equations. This is the matrix The matrix stuff is on the bottom. The first line is what you do to equations, and the second line is the equivalent step that you do to rows in a matrix. So you would use equation 1 to eliminate x1 from all equations below it. So that's what we did. We used equation 1 to eliminate the x. And that is use row 1 to eliminate all entries in the first column below row 1. Then you use equation row 2 to eliminate all entries in the second column below row 2. And you just keep doing that, working left to right. All right, so in your group activities, this will guide you through like step by step, each step of the algorithm process. So don't feel like you have to, write down this system of 3 equations, 3 unknowns, and like solve it and know how to do it with the matrix. First, write down the augmented matrix. That's just the matrix with the line. And then the next several questions walk you through the algorithm for how to solve it. So you can go ahead and start that. Let me know if you have questions. I'll help.